Good morning. Thanks for this opportunity to talk about the project I've been working on with Sergey Dubovsky, Gabriel Kama, and other collaborators. This talk will focus on the weakly coupled string description of a Yang global, which is a rotating folded closed string. I will assume large n limits so that we won't have any string splitting, and I will assume large J, so we can have one more J expansion and here from perturbative calculation. To start, I want to describe this effective string theory that we've been working on. Its action consists of a bulk action plus boundary terms. The bulk action has a derivative expansion that breaks down close to the endpoint singularities where energy becomes comparable with the string scale. And to cure those similarities, we add these boundary actions. To make it more clear, assume we have an open string with large spin. Its classical background would have this target space coordinates where omega is the power of -1 is proportional to the square root of j. It gives rise to rigid trajectory and has the following metric. You can see that the higher order derivative terms become singular due to the metric singularities. For example, the first non-zero term in the derivative, x curvature to the power of 4, becomes singular at sigma equal to minus or plus 1 at the endpoints. The boundary action that we add uses the boundary metric, and up to the first subleading order, it has only one non-redundant Wilson coefficient, and this gives rise to correction to the spectrum at the order of j equal to j to the power of -quarter. On the other hand, the bulk higher order derivatives also give rise to corrections to the spectrum, and this correction will be at the same order. The result is that higher order bulk contributions could be thought of as renormalized boundary Wilson coefficient. So we have this effective string theory for open strings in hand, and now it's time to glue two of these open strings and make a closed string. Up to the leading order, this means gluing the endpoints and fixing the endpoints on top of each other. And the bulk action would be the sum of the bulk action of each of these open strings. But if we look more carefully at the endpoints and add the boundary action, we see that this connection is not quite the gluing condition, the exact gluing condition you might assume. And its boundary action has an addition of non-redundant Wilson coefficient as opposed to open string that had only one Wilson coefficient. This boundary term gives rise to correction to some of the modes at the lower order, omega to the power of half, while in open strings, all the modes get corrections at the order of omega to the power of 3/2. For the rest of talk, I want to show you some lattice data and do some comparison. Before that, though, I have to emphasize that we have two different ways of describing this string description of globals. One is axiomatic string ansatz, or ASA, that assumes we have two open strings and then follow a tensor structure, which means we have to calculate the multiplicity of the states. For example, we have to calculate the multiplicity of one open string and then square it at each level. So the Hilbert space of the glue ball will be the sum of different levels, and at each level it follows a squared tensor structure, assuming that the left moving and right moving Hilbert space are the same as the Hilbert space of one open string. Axionic string that gets its name from 4D, where there are evidences to believe that we have an additional pseudoscalar degree of freedom on the worksheet. So we have to add this axiom that I will talk about more. The second way of thinking about this string description is to directly work with pose string. And in the vicinity of Reggie trajectory, these two ways calculate the multiplicity the same, but in higher levels, it's ASA that matches better with lattice state. For example, in 3D, already at the second level, effective closed string overcounts the states, while ASA calculates the multiplicities and also P and C parities of the states correctly. With our recent calculation and higher order corrections to close the string spectrum, we can also explain why the first pair of excitations on top of Reggie trajectory appear lower than what we expect. In 4D also, ASA seem more reasonable compared to lattice data, but there are some states that we cannot explain only by looking at the string excitations. As I mentioned before, there are evidences to believe that in 4D we have an additional degree of freedom, which is called worksheet axiom. And after adding this axiom to our calculation, we were able to explain all the states in 4D lattice data on the spectrum removable. Except for one state here at 3++. We also predict the existence of some more states which are heavier, and that might be the reason why we can see them in this data. Having more lattice data on 4D on the heavier side, we will be able to check our results further. Okay. To summarize, I described two different ways of looking at the string description of a student-yang global, axionic string ansatz, and effective closed string. Effective closed string overcounts the number of states, while ASA matches better with the lattice data. ASA assumes two open string attached at the endpoints, follow a tensor square structure. We developed an effective string theory that had band reaction that cures the bulk action singularities. Then we attached the two open strings to the closed string and calculate the balloon condition and these corrections. And with all that, we were able to explain lattice data in 3D and 4D, and also explain some mass splittings in 3D. The remaining questions, one of them is the parity assignment in 3D. There are some key parity assignments which are not determined only by assuming ASA. We are hoping that with our new techniques in hand, we might be able to determine those parities. I don't have time to talk about Mellon spectroscopy, especially because the stuff was focusing on globules, not mesons. But in our recent paper, we did comparison with meson spectrums, but there are more to be done there. And finally, there is always more to explore with the help of more lattice data. Thank you.
Thank you for a nice talk. Have 5 minutes for questions. Any questions? Yes.
Sure. So these are energy levels. And are supposed to be like horizontal. But when we look at the lattice data, we see that, for example, all of these pairs on even spin appear lower than this horizontal line. We calculated the corrections to energy of these modes, and the sign of one of the modes has to be negative. So it appears lower than this horizontal line. The other correction has a has a sign which can be determined by looking at this data, and as that state always appear lower than the other state, we can assume that that sign also is negative.
Is the slide extrapolated to infinite time or is it some fucking time?
These ones that I show here are kind of extrapolation to infinite n. But even for lower ends, the qualitative it doesn't change much qualitatively.
Because I was thinking that like the effective string is like appropriate to infinite time, so maybe you compare it finite time, maybe it's natural that there are fewer states.
Well, as I said, these are extrapolations. Of course, they're still finite, but even more, and the number of states doesn't change much. It's mostly the splitting that is different. So I still hope, especially for if you have more data on J equal to 0 and J equal to 2, we could see the more states that we expect to see here.
Is there any positive explanation why it's there? The first week.
Well, we have some explanation how this ASA model is different from quantization, but why ASA matches better with global? It's, I guess, mostly a phenomenological question.
We're comparing on this project.
Sorry.
This is for small project.
Yeah, so it starts from the 4 to 0, so in fact, extrapolate it with small speed. Also, I must say that the golden string calculation and ASA match with in this regime that we do most of the comparison with lattice data. So what we say is mostly in the regime that they actually match.
Any other questions?
Out of curiosity, so to understand these flexibility curvatures, suppress, along spines. And so in the large J expansion, when the string is like really one meter higher power of the curvature.
Well, for example, the multiplicity of states could be calculated only by looking at the leading order, where we don't have to be worried about that higher order terms in the bulk action. So as you mentioned, we can assume that we have this long string and we do calculation and we calculate the matrices. But we wanted to go to higher order calculations, so we had to look at the boundary more carefully, and then the higher order bulk operators appear in the same order, so we had to consider